On the morning of November 12, 2024, a telescope array in the Canary Islands locked onto a faint point of light moving through the constellation Ursa Major. The object was 3I Atlas, the third confirmed visitor from beyond our solar system, and it was entering a region of space where the rules change. Not dramatically, not suddenly, but in ways that are maddeningly difficult to untangle. The anomaly wasn't loud. It was a whisper in the data. A persistent mismatch between where the object should have been and where it actually appeared. Astrometric residuals, tiny offsets measured in fractions of an arcsecond, had been growing since late October, and by mid-November they refused to dissolve into statistical noise. At the same time, photometric observations showed something equally strange. The object's brightness curve was not behaving. It wasn't brightening as expected for a body at 5.2 astronomical units from the sun, nor was it fading in the predictable manner of an inert rock. It was doing something in between, something that resisted clean interpretation. And then there was Jupiter. 3I Atlas was passing within 0.80 of the solar system's gravitational anchor, and that proximity was not incidental. Jupiter is not just a planet. It is a rotating magnetic cathedral, a plasma engine larger than Earth's entire magnetosphere, embedded in the turbulent current of the solar wind. Its influence extends far beyond its cloud tops, out past the moons, past the ring system, into a vast and invisible terrain where charged particles spiral, magnetic field lines twist, and the very fabric of space becomes electromagnetically noisy. For a small, possibly active object passing through that domain, the question was immediate. Are we watching the object change, or are we watching the environment change the way we see it? If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. To understand what was happening, you have to understand where it was happening. Jupiter's magnetosphere is not a static bubble. It is a dynamic, breathing structure that pulses with the rhythm of the solar wind. At its outer boundary, roughly 70 to 100 Jupiter radii from the planet, lies the magnetopause, the pressure frontier where Jupiter's magnetic field meets the oncoming solar wind and fights to a standstill. Beyond that is the bow shock, a standing wave in the plasma where supersonic particles decelerate and heat. Inside, closer to the planet, is the plasma sheet, a flattened disk of charged ions and electrons co-rotating with Jupiter's 10-hour spin, creating a kind of electromagnetic weather that has no analog in Earth's neighborhood. 3 Atlas was threading this needle. Its trajectory brought it within range of Jupiter's gravitational well, but more importantly, it grazed the outer edges of the magnetosphere during a period of heightened solar wind activity. That timing mattered. In early November, a coronal mass ejection had compressed Jupiter's magnetosphere, pushing the magnetopause inward and amplifying the turbulence near the bow shock. For observers on Earth, this created a problem. Any dust or gas released by the object would interact with this plasma environment, becoming electrically charged, deflected by magnetic fields, and potentially rendered invisible or misinterpreted by ground-based instruments. Dust behaves differently here. In the inner solar system, dust rains are primarily influenced by solar radiation pressure and gravity. But near Jupiter, they enter a regime where Lorentz forces, the electromagnetic push and pull on charged particles, become significant. A grain that would normally drift outward in a predictable anti-sunward tail can instead curve, accelerate, or slow, depending on its charge and the local magnetic field orientation. This means that a traditional dust model, one that assumes simple ballistic trajectories, can fail. And if the model fails, the measurements it produces, brightness, color, spatial distribution, become unreliable. The background itself was also a problem. Jupiter is bright, not just in visible light, but across the spectrum. Thermal infrared from its deep atmosphere, synchrotron radiation from its radiation belts, scattered sunlight from its high-altitude hazes. For a faint object passing nearby, this creates a photometric minefield. Instruments designed to measure the object's light must first subtract Jupiter's contribution, and that subtraction is never perfect. Small errors in background modeling can masquerade as real changes in the object's brightness. By mid-November, Some observers were reporting a subtle brightening in 3i Atlas's photometric signal. Others, using different instruments and calibration pipelines, reported stability, or even a slight dimming. The disagreement was not dramatic, but it was persistent. And so the question sharpened. Was the object changing, or was Jupiter changing the way we measured it? Orbital mechanics offered one path toward an answer. Jupiter is an unforgiving auditor. Its gravitational field is so strong that even a close flyby, within a few OA, can expose tiny non-gravitational forces acting on a small body. These forces, if they exist, show up as residuals, discrepancies between where an object should be, based purely on gravity, and where it actually is. For 3 Atlas, the residuals had been flagged in late October, and by the second week of November, they had grown large enough to demand explanation. The standard suspect is outgassing. A comet-like object, even one as faint and apparently inactive as 3i Atlas, can release volatile material, water vapor, carbon monoxide, carbon dioxide, when heated by sunlight. That release is rarely symmetric. If the nucleus is rotating, or if active vents are concentrated on one hemisphere, the gas jet acts like a tiny rocket engine, applying a continuous thrust that nudges the object off its predicted path. This effect is well documented in active comets, and it is measurable. Non-gravitational accelerations on the order of 10 e to 10 O per day squared are common for small, active bodies. But 3i Atlas was not behaving like a common active body. The residuals were real, but they did not grow steadily. Instead, they appeared to fluctuate, sometimes increasing, sometimes plateauing, occasionally reversing sign depending on the observing geometry. Researchers at the European Space Agency's Near-Earth Object Coordination Center ran multiple orbit solutions, testing different outgassing models: isotropic jets, polar-aligned jets, sunward-biased jets. None of them fit cleanly. The residuals resisted simple parameterization. One hypothesis was that the outgassing was intermittent, turning on and off in response to solar heating or internal pressure changes. Another was that the jets were oriented in a way that made their effect highly geometry-dependent, becoming visible only when Earth's line of sight aligned with the active region. A third possibility was quieter, but more unsettling. The residuals were not entirely dynamical. They might be partly observational, artifacts of how the object's faint light was being extracted from the noisy, Jupiter-dominated sky background. By November 18th, after 2 weeks of intensive tracking, the orbital solution had tightened, but only marginally. The non-gravitational acceleration was estimated at roughly 3 Hogo-10 per day squared, with an uncertainty almost as large as the value itself. That was enough to matter, but not enough to explain clearly. Meanwhile, the photometry was telling a different kind of story. Or rather, it was refusing to tell a story at all. At 5.20 from the Sun, solar heating is weak, but not negligible. Many comets, even distant ones, exhibit some level of activity at this range, particularly if they contain highly volatile ices like carbon monoxide or methane, which sublimate at temperatures well below water's freezing point. Observers expected 3e Atlas to show signs of a developing coma, a faint, fuzzy halo of dust and gas surrounding the nucleus, detectable through slight deviations from a point source profile or through subtle color changes consistent with scattering by micron-sized dust grains. But the coma refused to appear. Images taken with the 10.44-meter Gran Telescopio Canarias on November 14th showed no measurable extension, no radial brightness gradient, no asymmetry in the light distribution. The object remained stubbornly point-like, even under excellent seeing conditions. Spectroscopic observations, conducted 2 nights later with the Very Large Telescope in Chile, detected no emission lines, no CN, no CA, no AHO, the usual molecular signatures of cometary outgassing. The spectrum was flat, featureless, consistent with reflected sunlight from a bare, dusty surface. And yet the dynamical data insisted something was happening. The orbital residuals implied thrust. The brightness measurements, though inconsistent across different observatories, hinted at variability. How could an object apply a measurable force without producing detectable gas or dust. One possibility was that the activity was real but faint, operating just below the detection threshold of current instruments. Another was that the dust grains were unusually large, too heavy to scatter sunlight efficiently, but still capable of carrying momentum away from the nucleus. A third explanation centered on composition. If the outgassing consisted primarily of molecules that do not fluoresce in visible light, such as nitrogen or argon, it could remain invisible while still exerting force. But there was also a fourth option, one that researchers were reluctant to state explicitly but could not ignore. The anomaly might be observational. The activity might be an illusion, created by the complex interplay between the object's faint signal and the electromagnetic and optical environment near Jupiter. By the third week of November, 2 independent observing teams had produced brightness curves for 3E Atlas, and those curves did not agree. The first team, using a network of robotic telescopes across the southern hemisphere, reported a gradual brightening of approximately 0.15 magnitudes between November 10th and November 20th. The trend was subtle but statistically significant, and it appeared to correlate loosely with the object's decreasing distance from Jupiter. The interpretation was cautious. The brightening might indicate an increase in dust production, possibly triggered by tidal stress or changes in solar illumination geometry as the object's heliocentric distance shifted. The second team, operating a high-precision photometric system in Arizona, reported something different: stability followed by a slight dimming. Their data, calibrated against a dense field of reference stars, showed no significant trend over the same period. If anything, the object was fainter on November 20th than it had been 10 days earlier. The contradiction was not dramatic, but it was real, and it forced a question that no one wanted to ask: which dataset was correct? The answer, frustratingly, was that both might be. Photometry is not a simple measurement. It depends on wavelength, on the filter bandpass used, on the phase angle, the angle between the sun, the object, and the observer. It depends on how background light is subtracted, how reference stars are chosen, how atmospheric extinction is modeled. Near Jupiter, it also depends on scattered light, on thermal contamination, on the faint glow of the Jovian magnetosphere and certain infrared bands. The brightening team had used a broader optical filter, one that captured more of the object's reflected light but also more of the sky background. The stability team had used a narrower filter, optimized for precision but potentially less sensitive to changes in dust color or grain size distribution. The phase angle had also shifted during the observation window, changing from 11 degrees to 8 degrees. A small change, but one that could alter the object's apparent brightness by several percent if its surface had any significant opposition effect. And then there was Jupiter. On November 15th, the object passed within 230 degrees of Jupiter's apparent position on the sky, close enough that scattered light from the planet's atmosphere became a non-negligible background source. Subtracting that contribution required assumptions about Jupiter's brightness distribution and limb darkening profile, and those assumptions varied between teams. The contradiction did not resolve. Instead, it became a constraint. Any explanation for 3 Atlas's behavior had to account not just for what the object was doing, but for why 2 competent teams were seeing different things. Timing added another layer of strangeness. In a simple outgassing model, cause precedes effect in a predictable way. Sunlight heats the surface, volatile ices sublimate, gas and dust are released, and optical changes follow within hours to days. But 3I Atlas did not follow that script. On November 9th, a solar wind stream arrived at Jupiter, compressing the magnetosphere and increasing the plasma density in the region where 3I Atlas was traveling. If the object was shedding dust, and if that dust was becoming charged by the plasma environment, this should have altered its optical signature, either by changing the dust's spatial distribution or by affecting how sunlight scattered off charged grains. Observers looked for a response. It appeared 3 days later, or it appeared earlier, or it didn't appear at all, depending on which dataset you trusted. The robotic telescope network saw a brightness uptick on November 12th, 3 days after the solar wind event. The Arizona team saw nothing unusual. A third group, using a space-based ultraviolet telescope, reported a faint, transient feature on November 10th, one day after the event, but the signal was at the edge of detectability and was not confirmed in subsequent observations. The timeline was scrambled. If the object was responding to environmental triggers, those responses were not arriving in a clean, causal sequence. They were scattered across time, across wavelength, across observing geometry, in a way that suggested either a highly complex physical process or a measurement system that was struggling to separate signal from noise. One possibility was dust lag. Particles ejected from the nucleus do not instantly reflect changes in activity. They linger in space, forming a trail that can persist for days or weeks. Observations of that trail depend on viewing geometry. When Earth is looking along the trail, the dust appears bright. When viewing perpendicular to it, the same dust may be nearly invisible. As 3I Atlas moved and Earth moved, the geometry shifted, and the apparent brightness could change without any real change in dust production. Another possibility was charging dynamics. In Jupiter's plasma environment, dust grains can acquire electric charge, and that charge affects their motion. A charged grain in a magnetic field experiences a Lorentz force, which can deflect it from a simple ballistic trajectory. If the charging process was intermittent, triggered by pulses of solar wind or by rotation of Jupiter's magnetosphere, then the dust distribution could change on timescales unrelated to the object's intrinsic activity. A third possibility was simpler and more sobering. We were watching an object respond to forces we weren't continuously tracking. Jupiter's magnetosphere is not a static background. It pulses, it rotates, it reacts to the solar wind in ways that are not fully predictable. If 3I Atlas was sensitive to that environment, then its behavior would reflect not just solar heating, but also magnetic conditions, plasma density, and electromagnetic noise that ground-based observers could not measure in real time. The timeline collapsed under scrutiny. Cause and effect became ambiguous. Researchers began to ask a different question. If 3I Atlas was interacting with Jupiter's environment, could Jupiter itself reveal the interaction? The idea was subtle. Instead of looking at the object for direct signs of activity, look at the space around Jupiter for traces of disturbance. If the object was shedding dust or charged particles, those particles would interact with Jupiter's magnetosphere, potentially creating detectable signatures, changes in local plasma density, anomalies in polarized light scattering, forward scattering spikes when Earth's line of sight passed through the dust trail, or even faint radio emissions from accelerated electrons. On November 21st, a team using the Atacama Large Millimeter Array attempted to detect thermal emission from dust grains in the object's vicinity. The observation was challenging. ALMA's sensitivity at these distances is marginal, and Jupiter's own thermal signature dominated the field. The data came back inconclusive. A faint excess was detected, possibly consistent with a small population of millimeter-sized grains, but the signal-to-noise was too low for confirmation. A second attempt focused on polarimetry. Dust scattering produces polarized light, and the degree of polarization depends on grain size, composition, and geometry. If 3I Atlas was producing dust, and if that dust was being deflected by magnetic fields, the polarization signature might differ from the simple Rayleigh scattering expected for an inactive body. Observations on November 23rd showed a marginal detection, roughly 2.3% linear polarization in the optical band. But the measurement was noisy and could not rule out instrumental artifacts. The cleanest opportunity came from forward scattering. On November 25th, Earth's orbit carried us nearly along the line connecting the Sun and 3I Atlas, creating a geometry where any dust in the object's sunward direction would scatter light strongly toward Earth. This is the configuration that makes comet tails bright, and if 3I Atlas had any forward scattered dust, this was the moment to see it. Nothing clear emerged. Photometry taken during the forward scattering window showed a possible brightness increase of 0.08 magnitudes, but the uncertainty was large, and the effect could equally be explained by phase angle variation or by changes in the sky background as the object moved relative to Jupiter. Jupiter was not revealing its secrets easily. The environment was loud, the object was faint, and the line between signal and noise had blurred. By early December, 3I Atlas had passed its closest approach to Jupiter and was receding. The orbital residuals had stabilized, the photometric contradictions persisted, and no definitive coma or tail had been confirmed. The investigation had not resolved. It had clarified what remained uncertain. The strongest constraint was dynamical. Something had nudged the object off its purely gravitational path, applying a force equivalent to a few billionths of a g over several weeks. That force was real. Whether it came from outgassing, from radiation pressure on a symmetric dust, from solar wind drag, or from some combination of all three, remained unknown. The second constraint was photometric. The object had not brightened dramatically, but it had not remained perfectly stable either. Different instruments, using different methods, saw different things. That inconsistency was itself a data point. It suggested the signal was fragile, dependent on measurement details, and possibly entangled with environmental effects near Jupiter. The third constraint was spectroscopic. No gas had been detected. No emission lines, no molecular bands, no fluorescence. If the object was outgassing, it was doing so in a way that did not produce visible light. The next decisive steps were clear. Tighter astrometry over the coming months would refine the orbital solution and constrain the non-gravitational acceleration. Coordinated multi-band photometry, using consistent calibration and background subtraction, would determine whether the brightness variations were real or instrumental. Spectroscopic follow-up, if the object remained accessible, might catch transient emission features that earlier observations missed. And time, simple, patient time, would allow the viewing geometry to change, revealing whether the anomalies were intrinsic to the object or artifacts of how we saw it near Jupiter. But underneath those technical tasks lay a deeper question, one that 3 Atlas had forced into focus. How do we separate an object from its environment when the environment itself is invisible, dynamic, and barely understood? Near Jupiter, the solar system does not simplify, it becomes strange. Magnetic fields twist, plasmas flow, dust charges, and light bends through layers of interference that no ground-based instrument can fully map. Every measurement is a negotiation between what the object is doing and what the space around it allows us to see. And so 3I Atlas remains, not solved, not mythologized, but carefully held in the space between data and interpretation. The mystery is not in what the object might be. It is in what we do not yet know how to see. Every interstellar visitor carries this lesson. The universe is not obligated to make itself clear. It offers signals, faint and tangled, and asks us to admit when the noise is louder than the answer. Something unusual could happen near Jupiter. Or it could already have happened, written into the data in a language we are only beginning to learn to read. The investigation continues, not with conclusions, but with questions that sharpen as the object fades back into the dark.